My name is Varis Sagir. I work as a Chief Technology Officer in Cisco Service Provider Business Unit. Today, I will talk about 5G and what are the main requirements from 5G transport perspective and what is Cisco's solution. So what are the key 5G use cases? And 5G has been talked about since about 2015, 2016 now. So I have been involved in pretty much most of the deployment in the world and has been involved in this transformation. The key use cases for 5G are three. One is enhanced mobile broadband. This is according to 3GPP. EMBB, this includes fixed wireless access. What basically it means is high bandwidth to the user. We talk about 1 gigabit per second to the user. What it means from transport perspective is increased bandwidth and capacity. The second use case is massive machine type communication, MMTC. This means scale and reliability. This doesn't require high bandwidth. It's more about scale, low bandwidth, but reliability is important. The third use case is totally new. This is the one which didn't exist in LTE at all. That's ultra reliable, low latency communication, meaning mission critical use cases. Basically, we are looking at service latencies of 1 to 25 milliseconds. That means you are looking at, just to give you an idea, today's radios only have a 25 millisecond of round trip latency. In this case, you're talking about the entire service to be 1 to 25 millisecond. What are those services? Augmented reality, virtual reality, tactile internet, there are multiple smart grids. Those are the use cases being defined there. What it really means is that network architecture needs to change. You have to push data plane to the edge, and that basically requires network transformation. And some of these emerging technologies, which I just talked about, from applications, entertainment, all those would require network change. So out of all these three, the first use case operators are deploying today. The third use case is the one operators are planning for it. This doesn't, as of today, there is not a use case which is being deployed in the world today for now, but it will be coming, especially with this new applications coming up. So if I break down what are the five major architecture pillars for 5G, what enables them, what changes are happening, the big one is NR. NR is 5G new radio. What exactly it means? Higher flexibility, higher bandwidth radio. When I use the word higher bandwidth, we are talking about massive MIMO. We are talking about a lot more bandwidth. And I will show you the calculation, how you convert these megahertz to the bits. And you see the difference is coming from LTE to 5G. Low latency, this is extremely critical. They're targeting 1 millisecond of radio latency to enable some of these services. So 5G NR is one of the most important thing in the 5G. And the interesting part is it is getting packet based. It is moving from the CPRI, moving from TDM to the packet based architecture. And we will talk about that, how it basically significantly has an impact. The second one is a big one, is the decomposition. When I use the word decomposition, what I mean is basically decomposition of radio. So for example, you had the baseband unit before, BBU. Now it's being broken into two components, CU and DU. CU stands for centralized unit, DU stands for distributed unit. Or the packet core, we use the word CUFs. Packet core was a single entity. Now you can divide into control plane and user plane. And we'll talk about that, why it matters. Because breaking them helps to push those components closer to the edge. And that will enable some of those new services. So decomposition is a big one. And then going cloud native. So the idea is, if you have something on-prem, you can put them in a cloud. All those workloads, CU, DU, packet core, they will all be container and hosting it in a general purpose hardware. Programmability is extremely important. Edge computing being talked about a lot. And I'll touch base upon this later in my slide also, how different workloads can be placed in different parts of the network. And then converged transport. Transport is the basically foundation which connects all those components together. It has to be extremely reliable. When I use the word converge, it has to be wireline and wireless both. It cannot be just wireless. And this is just because of the cost reasons. And lastly, to bring it all together, you need to have the closed loop automation, multi-domain. And another big terminology which has been talked about, and I will touch base also in my slide, is network slicing. This is something being defined, and basically you are dividing your network into logical networks to deliver specific services. So this is a 5G architecture. Some of these services, by the way, in ORAN been also being done for 4G. So don't be surprised if you see 4G workloads having decomposition and cloud native architecture, just like 5G. A little bit, I'm going to go deep into this RAN. It helped to understand when I use the word decomposition. Remember, I said baseband unit. Baseband unit is the radio controller, is the one which basically controls all the radio. So the decomposition we talk about is two components, CU and DU. The heavy lifting is done by the DU part. Now, today's LTE radios sits here. This is radio. This is the antennas which you see outside. And then you have what we call it as basically split 8. And it's based on CIPRI. CIPRI is TDM, time division. So either you have a traffic or you don't have a traffic, you will still see a traffic there. So CIPRI is not that efficient when it's doing radio. However, what's happening in 5G and the new radio standards which are coming up, they are going one split higher, meaning this lo-fi will be in your radio head, RRH. Why it matters? It significantly will reduce the bandwidth 10 times. And for this, we use the term split 7-2. 7-2x in ORAN, but it's a split 7 basically. So the protocols new, which has been defined, is eCIPRI, which is enhanced CIPRI, is an evolution of CIPRI. By the way, CIPRI is not a 3GPP standard. It is a forum which has Nokia, Ericsson guys have created this. ORAN, on the other hand, is the new promise that you can get the best of radios and best of baseband unit and best of radio out there with consensus of operators and vendor together. They have defined this split, which is called 7-2x. And then there's ROE, which is IEEE 1914.3. This split helps to reduce the bandwidth, and this split helps with the packetization of radio also. So what it means from a stack perspective, simple. As you go down the stack, it's good for radio, but bad for basically expensive for transport. As you go up the stack, the transport becomes cheaper. That's the main takeaway. As you go down, the latencies are strict. So another split which people talk about a lot, this will be mid-haul, which is called option 2 or F1, defined by 3GPP. And I will show you the deployment. This will be one of the most common deployment in the world. And anything above CU, we call it backhaul.
We actually have a question on Twitter from Rasmus Berkland. He wants to know, is it on the Cisco roadmap to integrate this 5G RAN technology into some of your existing hardware platforms, or is this still kind of positioned in a separate hardware category that's being aimed at a specific set of providers?
Very good question. These will be implemented by RAN vendors. This is not for Cisco Transport to integrate. It's basically will be an integration. If you have ORAN, like you have multiple RAN vendors or Ericsson, Nokia, those will be sitting baseband unit and DU, CU vendors. They will be bringing these components into their product.
All right, and thank you very much.
Yeah, so there is one component I will talk about later in my slide that we will be integrating, but it's a very specific component for a function. But generally, these is RAN vendor products, not Cisco. Now, since I talked about packet, so today when we are deploying CIPRI-based architecture, the general deployment way is to use passive DWDM or active DWDM. However, when you are deploying Fronthaul, it's not optimal to do passive DWDM. There are multiple reasons. They have issues with operations. You have to match the colors. On the other hand, we suggested that, hey, and the world is moving towards this, by the way, go to packet. Packet brings statistical multiplexing advantages, cost effective, topology independent, service visibility. So it's actually taking your backhaul, mid-haul architecture of packet all the way to the front haul. And that will significantly simplify the operations and will bring intelligence to the RAN network. And I will show you one example how we have done this in the RAN network, that part.
I just want to clarify what you mean by that, because I think what I understood you to say is that instead of all the towers, instead of purely it being an L1, L2 thing out there, that you're That you're injecting L3, that's transport via L3 to
Yes.
Fronthaul. That's what I thought I heard you saying.
That's what basically I'm talking about. Basically, it's a layer 2 traffic. You carry it in a SRBGP VPN and transport it to the baseband unit, and then you get all the benefits of fast convergence, and you can do a lot.
What does the underlay topology look like for that? What are the protocols involved in that transport from a routing perspective or from an L2 perspective?
So I will touch base upon that. Hold on to that thought, but I'll tell you.
Okay.
Yeah, so there will be L2 technologies because all the radios right now supporting L2 right now. They're not supporting L3. There is a roadmap for L3 though, but underlying technologies would be, taking L2, putting into segment BGP EVPN you can do in L2 and putting segment routing there. I will show you one stack later coming in.
I think there's some clarifications we should probably make because I don't know that a lot of the audience is going to understand or have experience with what the difference between DWDM and a packet front end is. So if you want to explain that a little bit, I mean, I'll give what I'm thinking is, in a DWDM environment, you're simply transporting wavelengths across a fiber, right? And then you have active equipment on either end that understands the frequency. That's where the matching color comment came in that you made. So basically, it's a color of light. The equipment has to understand that color of light, then be able to transcribe that, change that, convert that into Ethernet, because it's not Ethernet at that point. It's just wavelengths. So what you're saying is you're going to take optical wavelengths, which is specialty DWDM equipment, and you're going to instead use packet equipment in there, which is what a lot more folks are familiar with. So like, a router that can do MPLS or segment routing. I do want to make one clarification. Is in these environments, is there also optical equipment in there? Because a lot of these require the amplification that optical network will give as well. So is that still exists?
Nick, very good point. Fronthaul doesn't require amplification. These distances are less than 40 kilometers or less than 15 kilometers.
So at most, you're probably using standard long reach optics.
In fact, LR would be, and ER is a stretch in this case because it's just the latency. And I'll show you the next slide, which explains this thing. But just to clarify, it can be active, it can be passive. Passive is much cheaper, and that's why people use passive mostly. But you are on the right track, though.
A lot of this traffic back, of course, still requires layer 2. I think the traditional mechanism in wireless to accomplish that was using GTP. So when we're using SR carried layer 2 VPNs, are we able to now kind of benefit from some of the TE there that we couldn't necessarily get when we were doing GTP? Like from a flow hashing standpoint, is that able to allow us to maybe work a little bit better in a ECMP style fashion, or do we still suffer from a lot of the same issues?
So GTP, by the way, starts from DU to CU and CU to the packet core. This is GTP. We will still be doing load balancing. This is a Fronthaul. GTP is not there in the Fronthaul. Okay, so I'll touch base upon that topic, by the way, Chris, that how GTP and how we're going to move the workloads to get the GTP termination early. So this is very important to understand why the latency. So when you talk about Fronthaul, you are looking, by the way, all these latencies are one way. Your latency number is 75 microsecond or 100 microsecond. By the way, when I use the word hence, I mean Huawei, Ericsson, Nokia, Samsung. Okay, this is LTE latency when you're using ERAN. So 75 microsecond, and assume, by the way, 5 microsecond is for per kilometers. So there's not a lot of room for latency in this case. So your distances get pretty short. What I've seen globally, 10 kilometers is a distance, 15 is a stretch. With ORAN, however, that number may go a little bit up. With ORAN, that number goes to 200 microsecond or 160 microsecond, then you can go up to 30 kilometers or something. Okay, and so that's why I put less than 40 kilometers in Fronthaul. And there are different traffic types in Fronthaul. It's a VLAN tag user and control plane is a layer 2 traffic today. The packet size can be a jumbo frame in this case. Why? Because they would like to pack as many packets as possible. Synchronization plane is untagged multicast. Management plane is IPv6 or IPv4. 95% of traffic is user and control plane. Okay, there is a roadmap for vendors to put this in layer 3 It's user and control plane, but today it is a layer 2 traffic. That is the only layer 2 traffic in a mobile network today. Now, mid-haul or F1 is basically between CU and DU. That latency is a little bit relaxed, 5 millisecond to 25 millisecond. Okay, that's why you can use lit fiber. In Fronthaul, you have to use dark fiber. There is no, and that's one of the reasons Fronthaul will be very limited deployment as compared to mid-haul. Mid-haul will be like 60, 70% of the world. Fiber is very hard to get. Even the fiber-rich countries are struggling. In traffic types in mid-haul, it's all IP. And it will be the packet size can go from 800 bytes to 9K jumbo frame bytes. So, and the UE usually is around 1500 bytes of traffic. So that's basically, it's important to understand that number. That helps to dictate the distances you will see in the network. And I'm coming to the slide which shows all of them together. So I'll touch base on that. So this slide looks complicated. Don't worry about this. This is a packet core of control plane. This is a packet core for the data plane, UPF. Remember I talked about decomposition here. So Chris, to your question, GTP. So GTP termination is done by packet core. What it means is in a mobile network, if you do not terminate the GTP tunnel, you don't understand what the traffic is looking for. You have to terminate it on the packet core. Traditionally in LTE, these packet core were centralized, so you have to terminate that packet all the way. But do you know the percentage of traffic in mobile networks, video traffic percentage is 75% video traffic. So what UPF does is they break it. Now you can terminate the GTP tunnel on UPF. And once you terminate it, you can offload to the internet. That basically gives you predictability and get rid of all those traffic, which is service provider keeps on paying for this, right? So this is a packet core. And then second thing, what it's showing here is this is a RAN part of the network. What is important in this picture is all these interfaces are IP, all of them, except for the DU, I showed you the Fronthaul, which is L2 today. So this is something important to understand that IP is the way to go because all the standards have evolved to IP. Okay. Now this picture is a little bit more detailed, but this is all the architecture types which we talked about. Firstly, if you read this document, if you get a chance, ORAN Workgroup 9, this is the first time they have defined this. And Simon Sprague is part of my team. And he is one of the author of this document. In fact, he is the author of the document. So what we are showing here, CRAN, centralized RAN, which I talked about. So ORU, and then you have the router, which I showed you. And then ODU, which is sitting on a COTS hardware. This is the radio controller. And OCU may be sitting at a central site. You need dark fiber. And this is eCPRI, basically, a protocol which we are using here. So this is CRAN. As I mentioned, why people want to go for CRAN? CapEx and OpEx reduction. There is no baseband unit at cell site. It's a lean site, and that helps with spectral efficiency. It helps with gains. Another thing is CRAN, you can have a Fronthaul and a mid-haul topology also, meaning DU and CU can be put in different places. Why you want to do this? The reason you want to do this is because you want to keep the ODU because there's a one-to-many relationship there. So one CU can manage many DUs. Again, a form of centralization. Then there's another deployment which you will see. In fact, what I am talking to operators, most of the deployment will be mid-haul because you can see here, this will be a kind of a backhaul provider sitting in the middle. And then you have a transport network and you can put CU at a central site. Centralization helps with the resources perspective. The last one is DRAN. Today in the world, 95% of the deployment in the world is DRAN, meaning all these three components are at the cell site. That's basically is a typical deployment. And many of our packet core today are mostly centralized. However, in the new world, then you can put the UPF closer to the edge and terminate it and send it to the internet. That will enable ultra reliable low latency. There is no other way you can do this.
So I think I heard you say the EPC is going to be distributed now. So I'm assuming that's using, a cloud native architecture that you're using to distribute that, the EPC, whereas, traditionally that would be, somewhere else and becomes a point in the data plane. So does that mean the data plane is distributed as well if the EPC is distributed?
This is data plane distributed. This is UPF. That's the one which does that.
Okay. So in the underlay for that is IPv6 or IPv4 or both?
It can be IPv6 also. It can be IPv4 also. So it's basically up to the operator. And we are helping with SRv6, like some of the upcoming providers, they are going to use SRv6 to do that.
Got it. What's the, SRv6 has been a very, in the segment routing world, SRv6 has been a bit of a controversial protocol. What SR-MPLS versus SRv6, what do you see the advantages of SRv6 versus SR-MPLS for this application?
So you can use SR-MPLS. In the first phase, you will see a lot more SR-MPLS. SRv6 will be right now, few operators are looking at, as they're evolving their networks. Greenfield especially will be looking at that too. By the way, SRv6 topic, Kevin, will be touched in detail by Jose. He will talk about this. But in terms of scale, simplification, SRv6 basically provides a much better picture there. And obviously, if somebody's an MPLS, they move to SR-MPLS. So that's something is an easy transition rather than moving directly from MPLS to SRv6 for some operators. So it just depends where they are in the journey, what kind of expertise they have, what kind of comfortability the operator has. All those play into the picture. From technology perspective, both of them can do the job. SRv6 just provides better scale, and NFV and application programming. All those come with SRv6 too.
So one more question on this architecture here is in the design that you have. I'm assuming this is a mobility provider. It looks like a mobility provider to me. A lot of the mobility providers, and then you also have 5G fixed providers for just delivering bandwidth to a home or business. Does this architecture change at all if you move from mobility into fixed wireless? That's the beauty of this design, that you will have converged network. You can put wireline and wireless, fronthaul, midhaul. You can put ORAN, non-ORAN. It will be a multi-service network. In reality, you will not see just a pure mobile network moving forward just because of cost reasons. So to answer your question, no, it will not change. And that I'll show you the final converge what we have proposing. All the technologies remain same, and you can deliver both. Okay.
What about the convergence, especially for the fronthaul? So it is a layer 2. What you are doing for the convergence, high availability?
Meaning in terms of, sorry, I didn't get the question. You mean the layer 2 in fronthaul, how will we do the converge with it?
In case of failure, let's say, what would be the convergence there?
You get the same convergence. I'll show you a test which we did. We did a test in RAN networks, 0 packet, 0 call drop using TI-LFA. It does exactly the way the packet works. That's the beauty of this whole, and I'll show you this test. By the way, last thing I want to just touch base upon is this LTE will also be there. So it's not just 5G, it will be LTE, 5G, wireline, wireless, everything together. And we have ways to even transport CPRI in a packet. That we call it radio over Ethernet. So packetization of CPRI is another part of bringing the legacy into the existing packet network.
Now, considering in service providers, we have star topology between the DU site and the remote radio site. Why do you think DWDM cannot work in such point-to-point, topologies, basically?
It will certainly work. It's just the operationally challenging. It just gives you more insight. It gives you visibility. It gives you flexibility. It gives you fast convergence. Otherwise, it's just a dumb pipe. That's the difference. Working is not an issue. It's just a simplification.
But DWDM is more simplified than the IP layer. Do you agree?
But it doesn't give you insight. It's a pipe. So in DWDM passive, you have to match the colors, and it creates a big operational challenges. For people who are climbing towers, it's not a small thing. It's a cost. Secondly, you have no telemetry. You don't know what exactly is happening in the network. There's no fast convergence also if you have alternate path there. So those are the things overall in a network. If you are going there, it helps there in that case. And keep in mind statistical multiplexing. With eCPRI, you're getting packet. So with packet, StatMux comes in. Passive DWDM doesn't understand StatMux.
Yeah, why would you need stat multiplexing in a star topology where you have just point-to-point fiber?
Because then you have to put the interface accordingly. Because the uplink interface, the bandwidth which I'm showing here, you don't need to use the same bandwidth. You have to just use the peak bandwidth. So in that case, it helps. So So just one example of an operator going from LTE to 5G. So all these numbers, when I started working on that part, all these different megahertz, but the main thing is this in this picture to remember this. In 5G, this thing, bandwidth, that gets more. That's one of the big things you get there, 100 megahertz of channels. And in LTE, you can do carrier aggregation, but the chunk maximum is 20 megahertz. Number one, massive MIMO, 4G was more about, max 44 hours. By the way, guys, keep in mind, whatever MIMO you see here, your cell phone has to support that MIMO. Apple latest phone supports 44 hours. Latest one. Previous phone doesn't support any like 2 hours. Then you get massive MIMO with it. All these together means what? Fronthaul, you are looking at a bandwidth of 74 gigabit per second. By the way, this is a good big spectrum of 615 megahertz. How does it translate to my interface? I need a 100 gig interface. How does it translate to mid-haul bandwidth? You are looking at around 12 gigabit of bandwidth. How does it translate to a backhaul bandwidth? You are looking at 10 gigabit of bandwidth. By the way, keep this in mind. These numbers are at the higher side. In actual deployment, you don't see all the radios transporting at the same time. But compare this number with the average of LTE in the world. Average is 300 megabit per second. That's the average LTE cell site throughput. So all these numbers translate to one thing. Your access interfaces, when you build a network, went from 1 gig to 10 gig. Now it's 25 gig. 25 gig will be the new 10 gig in the industry. Everywhere, all the interfaces, devices, radio will have native 25 gig interface. You will have, if you are doing wireline and wireless together, you will be seeing bandwidth going from in a ring architecture can go up to, or point to point can go up to 400 gig. This is where Rana will talk about the RON architecture also, how that will help in this case. Then you have your edge and core. Since you have ripple effect of bandwidth, you will be looking at how the bandwidth will grow in the edge too. Point is this, when you are building these networks, when we talk about 5G increases the bandwidth, this is what it means by 5G increasing the bandwidth. And lastly, keep this in mind, 10 gig interfaces will be there in the radios, 25 gig will be there for massive MIMO, so you need 10 gig, 25 gig, 100 gig, 400 gig in different parts of the network. So when you are selecting transport, you need to take into account. Now, I did talk about data center coming into the picture. In LTE, there was no concept of any edge data centers. It's all centralized data center. In 5G, you may see far edge DCs. You may see edge DCs, regional DCs, central DCs. These two especially are expensive DCs. These are not regular data centers. These are maybe 3 racks, 2 racks, and they have really expensive. So you need to be very careful what you are putting there. Getting real estate is one of the biggest challenges. Now, all these workloads, DU, CU, so that's why people would be putting more DU at far edge DCs. They may be in 10,000. In edge DCs, CU and UPF, maybe in thousands. Regional DCs may be hundreds. But the key thing is, think about now you are managing those sites. So these workloads are not in hundreds, in 10,000 sites. So you have to take care of the cloud native architecture, or your management needs to take care of these parts. By the way, in a network, you may not see all of them. You may see some of them, but you will see multiple data centers. And that's how people will be deploying, depending on the service requirement. They need to place a workload closer to the user so that they can enable those services. So what I talked about, I'm going to summarize what you need from a 5G network. You need stringent KPIs. EMBB, meaning high bandwidth, low latency, densification, lower power, and reliability. The interesting part is this. Usually, either people do low latency or high bandwidth. Combining them together, that creates a big challenge. That's why you need flexible service placement in the network. That's one of the key requirements. Depending on, I think, Kevin, you asked me this question, wherever you want the workload, you should be able to place it without changing the network, your forwarding plane and your control plane. So IP is the basis for the entire thing for 5G infrastructure. Any-to-any connectivity, many-to-one relationship, all that will be there. 5G functions like RAN and mobile core are virtualized, so they need to be put in data centers. This is a highly dynamic environment when slicing, virtualization, CUPS comes into the picture. These components can move around, they can appear, disappear, and then different slices may require mobile components and different DCs to meet SLAs. Transport needs to support layer 2, layer 3 both. You transport SLAs for service and slices. It should be simple to provision, and it should be cost effective. So those are the high-level requirement what you need from 5G.
If I think back to the existing architecture, and especially and I work on RF networks quite a bit, but more around the packet, design side of the core and how that works and interacts with the towers. And one of the things that, is a current challenge that we solve with an extension in the routing protocol is if I've got GTP tunnels from an eNode B back to an EPC, and I'm bringing that back, and I want to do ECMP and routing, that's all kind of abstracted by the GTP tunnel. So there's an extension, we use in the routing protocol to be able to see the origin, of the traffic for the users, and then, use ECMP in the network. When you're distributing, and for life of me, I can't remember what the RFC is, but when you distribute the EPC like you are, how does that translate? If a segment routing or SRv6 is going to be my underlay, how does that make it from the radio to, does that change at all? Like, as if I want to be able to make sure that, if I need to, take a SID in segment routing and steer traffic, around the architecture to do traffic engineering, how does the packet core communicate with, either the underlay or the overall transport to make those kinds of decisions?
So Kevin, to answer your question, firstly, there's a feature, as you mentioned, GTP load balancing in Cisco routers. You need to enable it. For ECMP, it's not enabled by default. It's enabled for MPLS. You have to enable for MPLS. There are two modes, IP and MPLS. Both you need to enable. It doesn't change. So in terms of GTP, and by the GTP is used, the whole thing about GTP load balancing is it's always point to point because you have a radio, DU or CU. So GTP will be between mid-haul. Keep this in mind. There are two different GTP tunnels. DU to CU is a separate GTP tunnel. CU to packet core is a separate GTP tunnel. In both cases, you need to enable load balancing. It doesn't change. It's the same behavior.
Okay, so same protocol, same principle that we're going just on a distributed scale.
Exactly. We tried because we think that GTP is the one which is limiting mobile evolution. We are trying to get this replaced by SRv6. That will greatly change the game. And but anyway, 3GPP takes a long time. It's years of work, but we are pursuing that.
So it's been widely discussed that, especially with roaming, but in general with GTP being reasonably open, that there may be security implications of that particular technology. Is there anything that you're thinking about that addresses some of those issues that may come up? Because this is all packet based now. It's no longer,
Nick, there has been IPsec being recommended there, but that they have to do. You can do sec gateway, security gateway. You can send everything together. The challenge in general, I can tell you, especially in North America, there's not much. The security becomes a big overhead. But inherent, you can do it. You can do IPsec. You can look at MACsec. You can do technologies there. In general, only people are trying to do where they're going through a part of the network which is untrusted, they would try to do IPsec. If it's trusted, they would keep it on their own. It's just too much overhead to do these things.
And this is like the technology in general. It has nothing to do with Cisco or Nokia or whoever.
No, it's a general operational challenge. It's not as straightforward, and it's global, by the way. I've talked to many operators; they have all had the same issues.
Yep. So, it should be, like you said. Just to reiterate, there are mechanisms for dealing with it.
Absolutely, there are many.
All right. Thank
you.
So
how do we solve this? No problem. How do we solve this? How do we solve this entire thing which I just talked about? Our solution is start from the cell site all the way to your core network, having a unified forwarding plane, segment routing, MPLS or V6, doesn't matter, and unified service plane, BGP VPN. Why? And BGP VPN means L3 VPN or L2 VPN, depending on your basically traffic types. And then you need to, another thing to keep this in mind, that in 5G network, clocking is extremely important in the Fronthaul network, this part between radio and DU. Why is it important? eCPRI doesn't carry the clock. CPRI carries the clock. So everyone who is working in mobile needs to understand PTP and SYNCI, because without this, your radio will never come up. So there's a very good book written by a couple of my team members, Shahid Ajmeri and Dennis Haggerty. You should check out this book on Cisco Press. It actually, both of them have done this for 10 years, by the way. But timing is extremely critical in that part of the network. And then you have to have a trusted infrastructure. So that basically enables a very simplified end-to-end converged architecture with open interfaces. So that's basically our proposal, to not to change anything. And when I talk about network slicing, it will exactly use the same technology. So you're not changing anything and getting the same behavior.
Is there anything you guys are doing to try to work around running timing over mediums that might introduce litter? jitter, sorry. Specifically, when I think about running timing over transponders at higher and higher speeds, you need, FEC and things like that, which can actually introduce really small jitter, which can actually make P2P unviable across transponder links and things like that. So is there anything being worked on to address that?
In our transport routers, we are going for Class C timing everywhere. So Class C timing is the default which we are going with. That's what we are recommending. And then from packet perspective, PTP and SYNC and making sure that, we have all the standards integrated there. But I will get back to you on the transponder part.
We should probably define what PTP is, because I think a lot of folks that don't work in service provider and provisioning space probably aren't familiar with it.
Right. It's a 1588 clocking, packet-based clocking. The clocking is carried by packet. You can do this in two ways. You can put this, a GPS at a central site and distribute the clock, or you can put GPS at every cell site. The cost-effective way is doing distribution through a central site, but some people want to do it at the cell site also. That's also okay to do with that.
So for folks that are configuring equipment out there, this is very similar in concept to NTP. It's just significantly higher precision. The RFC is 1588, I think, right? And it's used a lot in DOCSIS networks and other, RF networks as well. So just to tie that into something folks might be familiar with.
And as I'm showing here, you can see that these globes and caching, offloading all your, Hulus and YouTube, which is 75-80% of the traffic in the world, which is continue to grow, putting your UPF at your, at your pre-aggregation site will significantly help with the bandwidth reduction also. So you can focus on different more services. So I am going to show you how, and this was a question I think somebody asked me, different traffic types. So segment routing can MPLS or V6, right, in the network. So when there's a layer 2, this part of the network, and Yiri, by the way, is going to talk about EVPN in the session later today. So we are using point-to-point VPWS in this case for Fronthaul. And that works out well with the underlay can be SR or SR MPLS or SR V6. But this Fronthaul is the layer 2 only traffic. But in Fronthaul, there are 3 traffic types, if you recall. There's a management traffic, which is L3. This is where you will use L3 VPN. There is untagged multicast that you don't need to worry about. Then in mid-haul and backhaul, as I mentioned, all of this traffic is layer 3. You use L3 VPN to do that, right? And then you need to take care of QoS also to make sure that you get the right queuing priorities to the traffic. Sure.
Because there's an argument we always have as network engineers. We go back and forth about, QoS and bandwidth. If I keep adding bandwidth, I don't need QoS, which is not something that I subscribe to, and that you need shaping. But if you're looking at, we're going to add this massive amount of fiber and this to the cell site and the tower, these massive speed increases. Why is the addition of bandwidth not enough? Where does the QoS come into play where it's not just bandwidth, but I need quality of service because of something that's not just a function of raw bandwidth availability?
Kevin, I have done this design with Tier 1. I had this debate with Tier 1 and I showed them why it matters. Very simply put, in a point-to-point, you will not, in a point-to-point, when you're doing this together, microburst comes into the picture. That's one reason. If you're doing in a backhaul and mid-haul network, fiber cut. That's what matters. When you cut the fiber, the traffic gets higher on the other links. This is where it matters. In a steady environment, everything is good. So that's what you need to take care of.
What about type of situation like earthquake, for example? When it happens, many people will just start using your mobile network, for example, and at the same time, and you want to prioritize some people over others, maybe hospitals, maybe police and those kind of people. So quality of service in those kind of situation also is necessary.
Yep, and radio management also matters.
Even in this slide, you're showing L2 VPN in the last mile and then L3 VPN all the way up to the core. So why not make it simple and have one L3 VPN end to end? So why are you recommending L2 VPN in the last mile?
No, it's just the matter where the traffic is terminating. In a Fronthaul management, because the management station is there, L3 VPN is actually there between ODU and ORU. But since the Fronthaul, I'm just showing the management plane, and management plane needs, the ORAN management itself is setting some application. But actually the VPN is ending here, ODU. The traffic has no significance after ODU.
Okay.
Make sense?
No, in the Fronthaul, you are saying, yeah.
The Fronthaul, this ends here, ODU. It's just the application, that application IP, because somebody, ORAN management needs to take care of this. But actual traffic ends at ODU. This has no significance between ODU and OCU.
Okay, clear. Thank you.
So this I want to show you quickly. This is the one I talked about. This is a test we actually did with Ericsson radios. Pretty cool. As what we did is we had this 6630. This is 5G radio, AIR644 rated. This is the first time we did the test that in a RAN network, we did the fast convergence using packet. We used TI-LFA, and what we did, we had this call running voice and video, and we cut the fiber. Guess what happened? Call runtime, there was no call downtime for 37 minutes because we ended the call. There was no cell went down because cell is the one which we looked at. So that is something which we proved that, and keep this in mind, radios also have buffers, by the way. So that's what we proved, that RAN networks needs to evolve. RAN network needs to go packet. And that's where you get a lot of new technologies and innovation coming in. Today, it's just TDM. Okay.
Would this allow me to get rid of ERPS as well if I'm doing like a Metro E style?
Absolutely. Absolutely. So another big change is happening in the network is the operators, which Dish recently announced, they are putting workloads in cloud, like OCU, like UPS. They're putting in cloud there, like AWS. This is where we are positioning a solution. You can do cloud-agnostic networking, putting a virtual like XRV 9K router. What you can do is, remember I talked about segment routing in the on-prem? You can actually extend all the way to the on-prem and off-prem and move it all the way to the cloud. And we have a solution for that. And once you publish the white paper, you can see it. But the key takeaway is your workloads can sit anywhere. And in infrastructure hosting is different in cloud. And that's why you need to take care of overlay routing to do that part. And we have and that's what we are implementing in Dish. 5G requires all the changes what we talked about. We have tried to make it simplified. Time-sensitive networking, TSN, is there, but TSN is actually good for in a dual traffic types. In reality, it doesn't add that much value when you have a single traffic type, and it just gives you a benefit with a 25 gig interfaces with 5 microseconds. So we have implemented this in our portfolio, and you will be seeing this coming up. And we already are supporting this in our portfolio. So network slicing in general is exactly the same solution we have with packet-based, because we think that network slicing, you don't need to change it. It's a shared resource, and it helps to deploy the same thing. So whatever I have talked about, you can do this in network slicing too. So all in all, this is basically a kind of the simplified converged 5G SDN transport from Cisco. Tom.